It's
Good morning.
it's evening over here, but I'm very happy to be speaking to you about a subject which I find fascinating. Why does mathematics work so well in physics? And this is actually a question that Eugene Wigner posed in his lecture in 1959 at New York University, where this should be on. The slide should be on. I'm speaking from that. This is a lecture that he gave on the 11th of May, 1959 at New York University. Eugene Wigner got the Nobel Prize in physics, and he invented the use of group theory in quantum mechanics, which was an exceedingly powerful tool at that time for investigating the spectra of complex atoms. And group theory came out of the blue. Nobody prior to him had thought of using it because it was just supposed, it's something so esoteric. It was something that pure mathematicians had fooled around with for a century, and nobody thought it would be useful. So Wigner, now that he came across this mathematical invention, he was ruminating on why mathematics is so powerful in this. And I'll take a couple of quotes from his lecture. The miracle of the appropriateness of the language of mathematics for the formulation of physics is a wonderful gift which we neither understand nor deserve. Wow, that's a very powerful statement. He calls it a miracle. And he says it's a gift which we don't understand because we didn't invent mathematics for physics. We do mathematics for its own reason, not to explain the world, but because we find it is a logical system that we love to play with, and mathematicians have a great time doing that. But it wasn't invented for understanding the physical world around us. And maybe mathematics is something that we don't deserve. A second quote that I'll take from him, he says, "It is difficult to avoid the impression that a miracle confronts us here, or the two miracles of the existence of the laws of nature and of the human mind's capacity to divine them." Now let's reflect upon this a little bit. Two things are being said here. That nature is run according to laws, that it's not fickle, it's not accidental, it has very well defined sets of principles which are inviolable. Why do those laws exist? We don't have a clue, but when we see regularity, then we are led to deduce the existence of laws that govern the entire physical universe. Then the second part, he says this too is a miracle, is that we are able to understand those laws. Suppose laws existed, but those laws were too complex for the human mind to understand them. Think of it this way. Okay, there's gravity, there's electromagnetism, there are all the laws that Newton discovered and Einstein discovered and so on and so forth. But if we had the brains of a cat, would we be able to understand those laws? No, because it's the human mind which is equipped, only the human mind so far as we know, which is equipped to deduce and to understand the laws of nature, and then, of course, we have used them to utterly transform human existence itself. Where we are going, we don't really know. Okay, now, let's come to why mathematics and physics are so hard for ordinary people to understand. It's because they're about abstraction. They're not about real things. The whole idea is that we look at things and we abstract from them and raise it to a higher level where where we are talking about things that don't exist. And let me tell you, have you ever seen a point? I mean, a mathematical point? I haven't. But you know, when I was in school, the teacher went to the board and she took a piece of chalk and she made a dot over there and says, that's a point. Well, fine, but that point was made by a piece of chalk, and if you look at it closely, the little pieces of chalk, and let's say that you look at just one piece of chalk over there, well, if you took a microscope, it would become bigger and bigger, and you'd find that there are atoms in there, and in fact, an atom does not have zero volume. It's not a point. It's something that a point does not actually exist. You can imagine that there is such a thing as a point, but then it's something that is a part of your imagination. It's not true. There is no such thing as a point. There is no such thing as a straight line in actual reality. So if I was to go to the board and I was to draw a line like this, then what would you say? Yeah, that's a straight line, but look at it from close, as I am looking at it now, and it's not straight. You see, my hand wasn't steady. All right, so then you say take a ruler, but a ruler is also going to have jagged edges. Point is, there's no such thing as a straight line. There's no such thing as a circle. A circle is by definition a bunch of points all at the same distance from the center, but I cannot ever draw a circle because physically it's impossible. But now think about this. How many lies have we been told in learning physics? We are told that, let's recall Newton's law of motion, that a body will continue moving if no force acts upon it. So it'll move at constant speed unless a force acts upon it. That's Newton's first law. But hang on a second. It doesn't make sense because suppose I take this body and I take it, all right, here there's gravity, that whatever I have will fall down. But if I was to take it in space, all right, the pull of gravity from the Earth would become less. If I take it further and further, it'll become less and less. I could take it, let's say, out of the solar system, but even then it would have some gravitational pull from the sun, from the other planets, and so in fact, there is no such thing as a free body. And yet all that we've been told is that F equals ma. Well, F equals ma, but F can never be zero. And so we have to imagine, we have to abstract. And so this is what physics is all about. But now let me come back to mathematics and tell you why mathematics is fundamentally abstract. So we talked about the point and the line and the circle, but let's talk about something even more basic, and that is the idea of numbers. We're used to counting 1, 2, 3, 4, 5, 6, etc. Okay? And then we say, well, what is this? So it's 1 apple, 2 apples, 3 apples, 4 apples, etc. 2 apples and 2 apples together make 4 apples. And so we think that the number 2 then is real. But it's not real. It's an abstraction. It's something that we have invented with our own minds. There is no such thing as a number in real life. It's a construct of your mind. It's something that exists only over here. All right, you'll say, then what is a number? And I'll say, a number is an object that obeys certain rules, like if you take one number A, you add another number B, then it doesn't matter if you add them in the other direction, in the other order. So 2 plus 3 is the same as 3 plus 2. Fine. That's a rule. And numbers will obey certain rules, a multiplication rule as well. A times B is B times A. So 3 times 2 is 2 times 3. These are rules that define the numbers that you use all the time. But you see, they don't apply only to integers, they can apply to non-integers. So for example, suppose A was 4 over 3 and B was 9 over 2. Well, 9 over 2, then you can add it in this order or that order. And so the numbers are defined by rules. They are inventions of the human mind. Now maybe I need to give you a little more proof of this. Okay, so let's take this as an example. Suppose I ask, what is the number which when multiplied by itself gives you 4? And you'll say x is either 2 or it is minus 2, which is fine. 2 times 2 is 4. Minus 2 times minus 2 is 4. But, and I know many of you know the answer because you're all college teachers. And obviously, this will not satisfy that, that will not satisfy that. But then, this is where the imaginary number had to be invented, otherwise you would not be able to solve this equation. And you know that for this, you have to invent what is called the imaginary number I, which is the square root of minus 1, which is defined by the following, that if you square it, it gives you minus 1. And so here is an example of a number that has been created by this thing over here. Well, this is 300 years old. Imaginary numbers then are defined by this rule. Further, they're defined by rules such as this: a plus b is equal to b plus a, and a plus a into b is equal to b into a, etc. Now, here is a number that didn't exist. We brought it into existence. We then said that you can take numbers like this, and so we can make numbers like this, 3 plus 2 times iota. That's called a complex number. You say, why do we need a complex number? Well, actually, we do, because you wouldn't be able to solve an equation like this, x squared minus 2x plus 7 equals 0, unless you had, well, maybe this has to be that. So this could not be solved unless we had invented this. Now, what does this have to do with physics? A great deal. Everybody knows that quantum mechanics is the great invention of the 20th century. Without quantum mechanics, people would not have their mobile phones. Without quantum mechanics, we wouldn't be able to understand how electrons move inside solids. So the transistor could not have been invented. The laser could not have been invented. We could not have understood the spectra of atoms. Our understanding of the world around us would be very, very limited if we didn't have quantum mechanics. And quantum mechanics cannot be done without complex numbers. Let me explain a little bit about that. So, in quantum mechanics, you have the wave function, which is denoted by psi. Everything that can be known about a system is in this quantity, which is the Schrödinger wave function. So let's take the simplest case, which is that of a single particle. Just one particle which can move in one direction only. Now, the amazing thing which was discovered back in the 1920s, so that's 100 years ago, it's about 110 years since quantum mechanics was invented. But before this, we used to think that a point particle could be, its position could be known, its speed could be known, both things simultaneously. But then this leads to paradoxes. It leads to things that are completely ununderstandable. For example, if there's an electron and is going around in a circular orbit, then according to classical physics, it should be radiating energy all the time, and so an atom should collapse. We should all collapse immediately. So why is it not happening? And this is where Schrödinger and Heisenberg come along, and they say an electron is not like the kind of particles that we are used to. They obey the uncertainty principle. Behind the uncertainty principle is this thing psi, which is a complex number. And so you can never see psi, but you can see this quantity, which is the complex conjugate of psi times itself. This is what is called the probability density. And so you can say that where the electron is most likely to be, the probability density will be high, and where it's never to be found, this quantity here and this will be 0. The wave function obeys an equation, and that equation is this. there's a certain constant which is called Planck's constant divided by iota, the imaginary number. Don't worry about this because this is, I'm not going to talk about quantum mechanics any more than this. My point here is this iota occurs here. You could not do quantum mechanics without imaginary numbers. So those things which you thought of as completely unnecessary, just inventions of the human mind, are actually fundamental to understanding nature itself. And now I'm going to tell you of some other things, and you'll see the importance of this. So can I have the slide? I want to go back to 240 BC. So that is, 23 centuries ago. There was this Greek philosopher, mathematician, Apollonius, living in a place called Perga. And he started asking this question. Suppose I have a cone, like an ice cream cone, and I cut it. So you see that here it has been cut in a way so that there's a circle that's been formed. But he could cut it. Let's see if I can change the slide. Yeah. But it can be cut in a slanted way. And what do you see over here? An ellipse. All right. But it could be cut into yet another section. And this is what gives you the parabola. And this is another way, the hyperbola. Now, my goodness, this is 23 centuries ago, and this was just for the love of it. This is the beginning of analytic geometry. And Apollonius didn't have a clue of why it would be useful, or if it would ever be useful. He did it because he so enjoyed doing mathematics. And 20 centuries later, you see an ellipse over here. Isn't that fantastic? With one focus being the sun and the planets going around it. The laws of planetary motion that Kepler deduced, and Kepler is at the time of Newton. Newton is 400 years ago. So Newton then looks at Kepler's laws of motion, and he figures out the law of gravitation. Now, that's okay. So Kepler made the observation. He didn't understand why this is moving in an ellipse. But once Newton starts looking at it, he says, my goodness, could this be the same force between the sun and the planet as the force that pulls an apple down to the ground? And that's then the beginning of the scientific revolution. The scientific revolution, which began 400 years ago, begins with the motion of the planets. And it brings to us the first inkling that gravity is a force that acts between two massive objects. And Newton wrote it down in the form of a law. The force between two masses is the product of the masses divided by the square of the distance between them. Okay, so now this is the this is the old way of looking at things. By old, I mean the way that Newton looked at it. He said there's a force between two masses, which is the product of their masses divided by the square of the distance between them, some constant g, which naturally we call Newton's constant because he invented this law. By the way, do you think he invented this law or did he discover this law? So that's a very deep question, but we'll come back to that. So this is the old way of looking at things, and together with this has to be an equation for what a force does. And that is the following. F is equal to ma. A is the acceleration. But these two equations by themselves, don't look very interesting or meaningful, I'd say, unless you have an understanding of what motion itself means. And so Newton invented calculus. This A over here is the second derivative of a function of time, acceleration. Together with calculus, this then gives you the planetary trajectories, it gives you the ellipse, it gives you the parabola, it gives you the hyperbola, and all of these things are trajectories, astronomical trajectories that have since been calculated and calculated very, very well. But now we come to a different thing. That's the way that Newton looked at it. But then comes along Einstein, and in 1916, he writes down the general theory of relativity. Einstein looks at gravity in a completely different way. And here, I'll have to do some hand waving because, in the few minutes that we have with each other, it is not possible for me to explain this in any detail. But think of space-time as being like a mattress which is flat. But when you put a mass upon that mattress, so let's say that you put a ball, then what happens is this mattress, which is flat, develops a kind of curvature over here. The bigger the mass, the more this is curved. Okay, now if you were to put a second mass somewhere further out, let's say a smaller mass, you would have two masses, and they would be inclined towards each other. And so if nothing else was operating, this mass would want to come towards this depression in the mattress. That was Einstein's way of looking at gravity. And Einstein wrote this down in the form of an equation. It's called the Einstein's equation of general relativity, which I will write down for you but will not explain. What it says is very roughly speaking, This R is called the curvature tensor. And this over here is called the stress energy tensor. So I'm not going to worry about factors like 8 pi or the speed of light squared, whatever. Just think of it this way. So this is a very, very complicated set of equations. It's actually 16 nonlinear differential equations. But written in this way, it's so beautiful, so simple. And what it says is the following, that whenever you have mass or whenever you have energy, so mass over here, then space-time will curve. And the amount of curvature will be proportional to how much energy or mass there is. And Einstein, look, when he wrote down this thing, he also proposed a test for his theory, which is that if this is the sun, and if light from a distant star passes by the sun, then this sun, which is very, very heavy, will curve the space-time around it, and it will cause the light to bend. And I've drawn it by a huge amount, but it'll be a very, very tiny amount, and it can be observed at the time of a solar eclipse. So in 1924, I think, Eddington went all the way from England to Australia to observe the solar eclipse and to measure exactly how much the light bends, and he found that was exactly what Einstein had predicted. And so Einstein became the most famous physicist of his time. In fact, when he went from Germany to America, to New York, 5,000 people went to New York Harbor to receive him. He was absolutely he was a celebrity even then. Anyway, the point is that here is an equation which expresses a very deep fact about nature itself, that whenever you have mass, space-time around it bends. And actually it bends around this piece of chalk also, but only by a very little amount because this chalk is so light. But this equation also gives you the black hole. I mean the real black hole, not where we are right now. Those black holes actually curve space-time so intensely that nothing can leave them, including light itself, and all this is contained in this equation. Now you say, my goodness, but this equation is so simple. How can it tell you so much? The reason? Because so much mathematics is hidden in this definition over here and over here. And I haven't even told you what a tensor is. These are things that one learns in physics. But I have to tell you that now you can teach this to students, to graduate students. But Einstein, when he invented this, he didn't have access to these ideas at all. He was thinking about the nature of gravity, but he could not have done it by himself. However, he chanced upon what this mathematician, Riemann, Bernhard Riemann, who was German, he had done work on, he had invented the subject of what is called differential geometry. and the geometry of curved surfaces. Now, Riemann didn't talk about space-time. He was talking about surfaces, and these surfaces, so like the surface of a sphere or the surface of a football or the surface of the sofa around you or the chair or whatever, these are curved surfaces, and he wanted to understand how to describe the idea of curvature. I have to tell you a story about Riemann. So, you've probably heard of the very famous mathematician Gauss. Gauss was an incredibly bright young boy, and he was 7 years old when his teacher decided to punish the whole class. And as punishment, they were told to add numbers 1 plus 2 plus 3 plus 4 plus 5 all the way up till 100 and get the answer right. So all the kids, because the whole class was being punished, all the kids were adding this up, and they got answers, but they didn't get it right. But Gauss, he was, in just 2 minutes, he had his head up, and the teacher said, have you added up all those numbers? I said, yes. He says, here's the answer. How did you do this? He says, ma'am, very easy. All I did was, I took the average of 1 and 100, I divided by 2 and multiplied by the number of numbers, 50. And so that's 101 over 2 into 50, and so that's 25 into 101, and gave the answer, 5,000 something. So the story is not about Gauss, but Riemann. So Riemann was a boy from a village, a German village, and he came to Gauss, and he said, Professor, so Gauss was a very famous man by that time. Everybody wanted to do his PhD with Gauss. So Riemann comes to Gauss and he says, give me a problem, professor. So Gauss says, you know, there's something that I've been thinking about for a long time, but I haven't yet succeeded. So then he gives Gauss this problem. He says, for 1,000 years, people have been using the assumption that parallel lines do not meet with each other. If you look at a railway track, they always are parallel to each other. But I want you to go beyond Euclid and don't use Euclid's fifth assumption that parallel lines will never meet. I want you to create a mathematics which so far does not exist, which you must create, and in which curved surfaces are, which describes curved surfaces. So Gauss gives this very, very hard problem to a village boy. The village boy, he is utterly frightened. He goes back to his village and he has a nervous breakdown. It's a very hard problem. But then 2 years later, he comes back to Gauss and he says, I've solved the problem. And here he lays out the idea of curvature, of how to take a manifold and to describe this in terms of calculus, and how when you go from one part of the manifold to the other, the angles then change from here to there. And Gauss looks at this and he says, very good, he got his PhD. Einstein would never have discovered the theory of general relativity without the work of Riemann. So Riemann, who did it for reasons of mathematics, No other. He was attracted to a problem that had its own interest. And that's how we got to this equation over here, which, by the way, is so useful that, if you use GPS without using this, you will get lost, because unless the curvature, unless the time delay which is predicted by this is included in the computers that are used to calculate where you are and to predict where you will be, you would then be going you'd be going wrong everywhere. And it is this also, even more importantly, if this is the equation which tells you that the Big Bang happened, that there is no center to the universe. Even though the Big Bang happened, it happened everywhere. So these are incredible things, very, very powerful things, but they came from mathematics itself. So now I want to go back and show you a few more slides. So back in the days when I was learning physics and mathematics, we were told that all the mathematics that you need for physics is the following. Calculus, let me put this down over here. So you need, of course, calculus and linear algebra and differential equations and complex variables. And then they said, you can also, you should study probability theory and do some group theory as well. But that was 50 years ago when I was a student. And this is all that used to be taught in the physics department. Now, if you want to do theoretical physics, you have to know a lot more. You have to learn about differential geometry. You know the stuff I just talked about that Riemann invented? You have to learn that. You have to learn what is called differential topology. I'll tell you a little bit about that. Other things, fiber bundles and knot theory and things that I don't know really. I can read them, but things have moved on. So the question is, it takes you years to understand this, but does this really help? And let me try and convince you that it does. Let's go back 150 years ago. And this is the time of James Clerk Maxwell, who was then living in an age where new discoveries in electricity had been made. So starting with Faraday, who noticed that an electric current, if it passes by, disturbs a compass needle, and says, my goodness, there's a connection between the passage of electricity and the creation of magnetism. There was Lenz and others. And so he lived in that age where these discoveries were being made, and he put them all together in what are called the Maxwell equations. Now you can see how complicated, he wrote this in a very complicated language. So there are 20 equations. Don't worry if you can't see them from where you are. But by the way, this is the same Gauss, which is mentioned here. Gauss, who was Riemann's teacher. So Gauss's law of magnetism, Faraday's law, Ampere, Maxwell law, he had these 20 ugly equations, which were first of all, even to write down 20 equations without making a mistake is not an easy thing. But then comes along an electrician. And just look at the dates. The original Maxwell equations were 1865. And this electrician, by the name of Oliver Heaviside, he's born 1850, dies 1925, dies, young man, well, not too young, but he's just a high school graduate. And he finds a new way of writing down the Maxwell equations. This is the University of Edinburgh, and there's a statue of Maxwell over there, and you can see that the equations are so much simpler. There's just 4 of them. In terms of, well, I'll read them out. The divergence of D is equal to rho. The divergence of B is equal to 0. Curl of E is equal to minus dB by dt. Curl of H is dd by dt plus J. J is the current density. But, okay, so those 20 equations, which were so long and so unwieldy, have been reduced just to 4 equations. And now you can see that, this is something very beautiful, that the amount of information hasn't been lost, but this has been written so economically and so beautifully that it's been reduced from 20 to 4. So this is what you will find on a mug. I have one of these. These are T-shirts that are sold in so many university campuses. Has something happened? Okay. And God said, let there be light. Well, where did the light come from? It came from Maxwell's equations. Okay, so let me back up a little bit. So now I can address the audience more clearly. So back in the 1850s or so, there was the question, how does light and energy from the sun reach the earth? After all, there's empty space up there. So how can energy cross those millions of miles without a medium being there? So some people then hypothesize the existence of an ether, some mysterious substance that was filling everything between the earth and the sun. Okay, but where's that thing? Nobody had a clue about it. Well, Maxwell was thinking of a very different thing, actually. He was looking at the equations that were known at that time, and he noticed that there was something not quite right. That if you use Gauss's law on those equations, that somehow charge would go missing. So to prevent the charge from being lost, he had to invent a new term. And that is the dd by dt. So it's what you saw earlier, you'll see again, it's that displacement current which came about purely mathematically. There was no physical reason to believe that it was there, but it had to be there so that charge would be conserved. And now that is what led Maxwell into predicting the existence of electromagnetic waves, that When a charge accelerates, so changes its speed or changes its direction, out will come waves from that. No need of the ether. Just these equations themselves will tell you that there has to be something that will carry energy onwards. So that was such a momentous thing, because now not only could it explain that energy comes from the sun to the earth, but then what if I accelerate electrons within a wire? Will that then lead to energy coming out? And that was the discovery of radio waves. And then, of course, in the next 150 years, everything around us runs on electromagnetic waves. So radio, television, laser light, all that is electromagnetic waves. And it came because an equation had to be fixed. So mathematics gave you the prediction of an absolutely new phenomenon. Let's get back to that. So let me see if I can. Yeah, this is the equation I was talking about, the last one, where it says curl H, del cross H is equal to J plus dd by dt. So the very last term is the one that Maxwell invented. He had to invent that to make his equations self-consistent and to preserve to have the conservation of charge. So we have all kinds of mugs that are sold on campuses over there. Steven Weinberg, who got the Nobel Prize in Physics together with Abdus Salam, he has such a nice thing to say. He says, if you have bought one of those t-shirts with Maxwell's equations on the front, you may have to worry about its going out of style, but not about its becoming false. We will go on teaching Maxwellian electrodynamics as long as there are scientists. So just like we'll be teaching F is equal to ma to our students, we teach them now, we'll be teaching them 500 years later, 5,000 years later, because that's not going to go out of fashion either. These are so strongly protected by observation, you see, if you want to send a spacecraft to Mars, and Elon Musk is sending them all the time, will be sending them all the time very soon, you don't even need Einstein's equations for that. Newton's equations, F equals ma, and F equals g m1 m2 over r squared, what I showed you earlier, that's good enough. You just have to solve the differential equation, and then, yeah, your physics doesn't change. Let me tell you about how we teach Maxwell's equations these days. And again, it's impossible for me to get into too much detail, but you saw those 4 equations here, for example. Yeah, they're nice, they're very nice, but you can write them as 2 equations now. And the first equation, in which you have 0 on the right-hand side, these are called the homogeneous Maxwell equations. And they tell you that there's no source term, there are no charges, it's unaffected by charges or by currents. The second equation tells you how charges and currents affect electromagnetism. You will agree, at least I hope you will agree, that these are prettier. Instead of 4 You have 2. Well, first we had 20. 20 was reduced to 4. Now 4 is reduced to 2. But you know, it's also the quality of the equations. And this guy doesn't like indices and coordinates. So you see, indices, there are the Greek indices over there, mu and nu. And really, can you find a way in which you are not dependent upon the reference frame in which you happen to be? Which means, can you find a way of writing down Maxwell's equations in a way so that it's applicable in every frame? And that then leads me back to Riemann. So Riemann, as I told you earlier, he was looking at surfaces, at how they curve, the distance between 2 points on a curved surface, the areas, etc. And is it? Yes. So the question here was, is it true that Riemann died at the age of 40? Yeah, he had some lung problem. He was already very sick when he came to Gauss. And I told you he had a nervous breakdown. His health was not good. At 40, he died. And well, he left behind a legacy of differential geometry. But then after a couple of decades, mathematicians moved on to something even more basic, even more fundamental, and they started inventing this new subject which built on the old, called differential topology, in which you worry about how many holes there are on a surface, whether this surface is embedded in a higher surface, and so forth. Now, with these things which are called differential forms and which owe to Riemann and the people who came after Riemann, in particular Cartan, now there's a new thing that they invented which goes under the name of differential forms. There's a thing over there, there's an operator over there which, if it operates twice, so d into d is d squared, gives you 0, the 0 operator. And it turns out that the calculus of manifolds becomes incredibly simpler. So what you see is topology coming into calculus, and this very fundamental theorem, which is still called the Gauss's theorem, but now it is written in a completely different language. Now that language will lead us to Maxwell's equations using differential forms. And here are the 20 Maxwell equations reduced to 4, reduced to 2, but those 2 had indices in them. Here are Maxwell's equations with no indices. No indices. This is true everywhere, everywhere, everywhere. And so you can use them on the surface of a black hole, inside a black hole, getting close to a black hole's center, wherever. You don't have to keep changing your frames. It's something that's true everywhere, everywhere. And now I'll tell you about the same thing, how this has to do with Einstein's equation. I wrote down Einstein's equation in the form of R is equal to G times T. But those had indices on them, right? Now, I'll come to Cartan. And Cartan, also a French mathematician, he said, imagine that I'm a cockroach. And I am walking on the surface of a sphere or some curved surface. Okay, now I'm carrying my own coordinate system with me. So there's a coordinate system X, Y, Z. All right, and as I walk along a path on some curved surface, my antlers will be here, there, my legs will be here, there, and this then leads to the concept of Vielbeins. So this is a German word. It's you pronounce this not as Vielbeins, you call it Vielbeins. I don't know why, but that's the way the Germans have it. And these Vielbeins, they move with the cockroach, and so the cockroach, as it maps out the entire surface, he's carrying his own coordinate system. So you can see that this is a surface that looks like a horse saddle, and you notice that there are two parallel lines, but these parallel lines are diverging from each other. Locally they are parallel, but globally they are diverging from each other. This omega is what is called a connection one form. Let me not explain this, but basically it's telling you how, when you go from one coordinate frame to the other, this omega connects up all of them. Why did this exercise have to be done? What did this buy for you? And now here is absolutely the simplest way in which you can write down Einstein's equation of general relativity. These, okay, you'll say, this is not as pretty because there are still indices over there. But these indices actually do not refer to particular frames, rather they refer to the cockroach itself. And so this is a very pretty way of writing down Einstein's equation of general relativity, which is valid everywhere. Okay, good. So I think now we can talk about this. I thought I'd talk a little bit, maybe we need a little time for question and answers, but I thought I'd talk about that, first of all, that all math is not science. Math is stuff which is logically consistent. You take a bunch of axioms and you deduce consequences from that. It doesn't have to be useful. And it's not always useful. So, for example, chess is a game that's defined by mathematical rules. And chess doesn't help you understand the physical universe. It wasn't invented for that, and chess simply is useless if you want to understand a physical phenomenon. So I've hopefully convinced you that mathematics is exceedingly useful for physics. But let me ask, do you think all science it comes from mathematics? No, absolutely not. Think of something like Darwinian evolution, which doesn't have a mathematical basis to it. It has an observational basis to it. And without Darwin's theory of evolution, we would not be able to understand the tree of life. We wouldn't be able to understand how living things evolved, how they grew how they acquired special attributes and so forth. but it doesn't have any mathematics to it. So you can have good science, excellent science, basic science without mathematics. And I should also say that mathematics is not useful everywhere. For example, does it help you understand the nature of feelings? I don't think so. You might have some psychologists who do some testing and they put their findings down in the form of numbers and so forth. But does it help you understand the nature of love? I don't think so. Is mathematics crucial for social science? Again, I think that social science, the very name science in social science, is probably not very accurate. And it comes because of the huge successes of physical science. Physical science, that transformed our entire way of thinking, starting from the time of the scientific revolution, from the time of the Enlightenment. So 300 years ago, it completely transformed our way of thinking because it was so powerful in being predictive. You could tell where the planets go. You could tell what happens if you do this or that to a physical system, on the basis of which we had the internal combustion engine, we had the atom bomb, etc., all that. So the power of prediction is what made science such a hot thing. But look, everybody wants to get onto this bandwagon, so those who studied anthropology or studied the way people relate with each other, they started calling them social sciences. So I'm not totally against the idea of calling them sciences, because there is an extent of rationality over there. But it's very different from the physical sciences. Well, maybe we could discuss that. Coming back to science and mathematics, which is the more powerful thing? Let's ask. Well, I think that's an unfair question, which I asked. In principle, you could have mathematics even if there was no physical universe. So suppose I take away all the chairs in this room and I take away all the people, and the mathematician has just a piece of paper, and maybe if he's smart enough, he doesn't even need a piece of paper or a pencil. He can create a system of axioms and then deduce consequences from them. And so you could have mathematics in a world without matter, in principle. Okay? Of course, the mathematician is made of matter, but now you can imagine a situation where AI comes along and that AI doesn't have a material existence here. Maybe it has an existence somewhere else. It can create mathematics without there being anything else around it. Well, maybe. But if one looks at the history of mathematics, then you see that it has been inspired by the physical world. Let's go back to Newton. Newton is told by Kepler that these planets are going around, and then his three laws, he puts them before Newton and he says, this is what I've empirically discovered. And Newton thinks about this and he comes up with this idea of gravity, and he has to invent calculus for that. So this is a mathematical invention which was inspired by a physical observation and then used to make a host of other observations. Or let's take the flow of fluids. So the Bernoulli brothers, they were looking at how fluids flow through pipes, and they made a lot of observations, but then how do you explain the flow of water, the flow of liquids, of gases, and so forth? And so out of that came differential equations which had to be solved in a particular way. So today we have Bernoulli's equations, for example. Or let's go back to gravity, and you saw this earlier, how Riemann's discoveries, inventions, then led to Einstein's formulation of gravity and so forth. So the point is that you should not ask which is more basic. The two have moved together. And in this day and age, if you look at those very top physicists, I'm speaking of people like Edward Witten. Witten won the Fields Medal for mathematics. So here is a physicist known for his work in string theory, and yet he is celebrated by mathematicians with what is really the Nobel Prize for mathematics. It's an incredible way in which new mathematics has been invented for working out the problems of superstrings. We can have a question later. Huh? I'm going to stop in 5 minutes or so that we can have questions. I've repeated Wigner's question to you, the unreasonable effectiveness of mathematics in physics. But there are very profound questions other than that. So, what is it that makes us humans capable of mathematical reasoning? Secondly, why is the universe understandable? We don't understand that. In mathematics, if certain quantities exceed a certain limit, then your equations become unstable, they become chaotic. Like, for example, the equations that describe weather are fundamentally chaotic, which means that if you make a little bit of error in your starting estimate, so today the weather is, okay, it's 17 degrees, the pressure is so much, the winds are so much. Can you predict what the weather will be like over here in Islamabad tomorrow? Answer is yes, to a very good approximation. We can say whether there'll be rain or thunderstorm or whatever. Can you do it 2 days later, 3 days? Yeah, by the end of the week, maybe to 30% accuracy. So 90% accuracy has decreased to 30%. But can you do it for 2 weeks? Answer is no. You can't do it because this is fundamentally a chaotic system. And so if you make a very small mistake in your initial data, the other side will be hugely different, and so you'll get nonsense. You'll get a nonsense prediction. Now the question is, why are we able to make such good predictions about the solar system, for example? I mean, we can tell where the moon will be 10,000 years from now. But if the gravitational constant had been bigger, let's say quite a bit bigger, then we couldn't have said where it will be the next day or the next week, let's say. In which case, Newton would not have been able to deduce the laws of gravity. We would not have been able to understand gravity. Forget Einstein, all that comes much later. But why is the world predictable? Or at least predictable to the extent that we can say so much about it without knowing everything. this actually brings up another interesting point. Suppose the world was entirely quantum mechanical. We know that quantum mechanics operates at the level of atoms, of nuclei, even of certain special systems like liquid helium. And these days, in the laboratory, you can have atoms create complexes called Bose condensates. But what if everything was in one wave function? That means that in order to know anything, you would have to know everything. But obviously, we can partition off things so that we don't need to know everything. We need to know some of this, some of that, in order to make a prediction. But why is it that way? I don't know. Nobody knows. And one last question, really, which is, again, nobody knows the answer of this. We have taken so many things for granted. We have taken, for example, that space-time was always there. All right, Einstein came along and he said, space-time moves according to how much matter there is. So the equation I wrote down earlier, R is equal to G times T. Okay, but hang on. This assumes the existence of space-time. It's that the curvature of space-time changes with the amount of matter, but where did space-time itself come from? This is an example of an emergent phenomena. And my very last question, unanswerable, is consciousness also an emergent phenomenon? Well, we know that a virus is not conscious. We see that cells have some degree of knowledge of where they are. We see that as you go up the evolutionary ladder to fish, to amphibians, to mammals, to primates, well, you see that animals become more aware of their environment, more able to deal with it. And then, of course, you come to us, humans. So, where did our consciousness come from? And is this an emergent phenomenon? Is this something that can be understood mathematically? And that is going to be the question for the 22nd century, the 23rd century, and all that. Right now is just a matter of speculation. So I'm going to stop here and get your questions. So we have a question over here, but let's, okay. So while, yeah.
Relationship between mathematics and logic.
So what is the relation between logic and mathematics? Mathematics relies entirely upon the existence of logic. And these are very deep questions which go into defining numbers. You could not. So logic is one step even further below mathematics. It provides the foundations of that. This is the work of Bertrand Russell and so many other people, Principia Mathematica. Yeah, let's have a question from Regina. We're not hearing anything. Is someone speaking over there?
Can I ask a question? Could you hear me?
Yeah. Now I can hear you. Yeah, okay.
Okay. My question is regarding AI and mathematics. So, how is AI going to impact mathematics, and is it going to evolve with the AI?
Okay. So AI and mathematics. Okay, what is AI? AI, if you're talking about neural nets, well, neural nets, they simply predict the next word or the next alphabet. And so large language models are probabilistic. But what you have now is AI using both algorithms and LLMs, large language models. And so, for example, if you go to Gemini and you ask it to do a problem in calculus, it will do that immediately. It has, so ChatGPT has two ways of thinking now. One that is the LLM way, the other is the algorithmic way. In the algorithms, it is programmed so that it works just the way as, let's say, Python does, or Mathematica, or Maple, or whatever mathematical program you use. Will this create new mathematics? If that's your question, and what I hear from the experts is no. It can follow rules because it is algorithmic while doing mathematics, but it cannot create something brand new. However, in terms of theorem proving, ChatGPT is already capable of that. And so a lot of proofs that would be very hard, let's say for me, for any mathematician, ChatGPT can help you arrive at that proof very, very fast.
Can you hear me, Dr. Hoodbhoy? It's
Yeah.
a pros here. Can you hear me?
Yeah.
Yeah. My question is the following. At the outset, you said that the line, point, they don't really exist, and they are mathematical entity or objects. So, but they use them to describe reality, though, that we know. So how do you relate to that? Something doesn't really exist, as you said at the outset, and describe something that does exist, i.e. the black holes and whatnot.
Oh, what I was saying is that there is no such thing as a point or a straight line, and that's an observational, that's simply true, because how can I make a point? Even if I take a pencil and I sharpen it and put it on a piece of paper, well, it has to leave a mark over there, a mark that I can see. And if I can see it, it's certainly made up of atoms. And if it's made of atoms, then it's not a point. So there is, in fact, no such thing as a point that exists in anywhere in the universe. It is entirely imagined. And then I gave you the example of a number whose square is -1. Where is it? Doesn't exist, does it? It exists only in your head. But it's useful. It's very useful. Here's the whole thing about abstraction. See, animals can't abstract. We can. We can write poetry. Poetry is also abstraction. You imagine something very beautiful. Does it actually exist? May not. Okay, you see something beautiful. Maybe it's the sky, maybe it's a girl, maybe it's what. And then you put those ideas in your head and you write some stanza poetry. But that's your creation. It doesn't exist anywhere except within you. Yeah, question
Sir,
from here.
Sir, my name is Masood, sir, and thank you very much for the enlightenment, sir. I have just three small points.
Just 1 second, because I think that has to be turned. Yeah, go ahead.
My name is Masood, sir. Thank you very much for all the enlightening talks, sir. I have 3 points, just your take on that. First thing is about this AI. So what I know is that now AI can do research on so many variables upon one dependent or independent variable that sky is the limit. So as such, the humanly capacity is being surpassed by the AI. Second, related to the quantum physics or what you were saying. So I heard just a few days back that there's a spaceship which has crossed 1 light year and still sending those signals, and it is based on that technology which was around 10 or 12 years before, and it is still functional, and it is getting Voyager 1, I think.
Yeah.
And so from that, I just want to have something, what is this quantum entanglement, etc.
Okay, so
And one thing more, sir. This Large Hadron Collider. So how this has helped the physics and mathematics, or has it combined them, or has it diversified them to the knowledge of all of us? Thank you very much.
So the first question is whether artificial intelligence will surpass human intelligence. And the way things are going, it seems likely that in many areas, it will certainly supersede us. In terms of, you see how ChatGPT answers your questions, how it does student assignments, which is a bane. But yeah, what will it do 100 years from now when computers are 1,000 times faster? All these are open questions. And so there does not seem to be any theorem which says that AI will not surpass us. People like Stephen Hawking were very worried that not only will AI surpass us, but unless rules are written into AI, that it could lead to them taking control of humans. Your second question was whether there is a spaceship that's a light year away from us that's sending us signals. Absolutely not. No. For light to travel 1 year from a spaceship would make it so dim that we would not be able to capture the light from that. What you might have heard of is a spaceship that was launched in the 1970s, the Mariner, which has now moved into a distant part of the solar system. It has not yet escaped the solar system, not gone beyond Pluto, but it'll keep going on forever now, because there's nothing to stop it, and where it will finally end up a few million years later, we don't know. Your third question was about the Large Hadron Collider and what implications does that have for physics. Well, there we smash protons against protons, and so so when we smash them at high enough energies, what happens is that we create the situation of extreme high density, high temperature, which is very similar to what existed at the very beginning of the universe. And so we've learned some physics from that. We've had confirmations of our theories of strong interaction physics. Has it led to any advance in mathematics? I don't think so. So this was built for the purpose of physics, and it has not led to new mathematics being created. That is the job of mathematicians. I said, mathematicians don't even need these machines. You can lock a mathematician in a room and ask him to generate new ideas based upon what he already has in his head. Let's take one from there. Yeah. Yeah. Regina, over to you.
You have a question from here? Anybody has a question?
Okay, then we'll take one from here.
Okay. There's one person here, Dr. Hoodbhoy. Go ahead.
Okay.
So could it be possible the reason why math is so good at explaining physics is that new math is being developed in response to physics? So we're creating new things to explain what we're seeing? Is that a possibility as to why they work so well together?
You ask for the reason why they work so well together? And what was the first part of your question? I missed that. Can you speak a bit louder?
Yeah, I can go to the microphone, might be better. Yeah, so my question is possibly one of the reasons why math is so good at explaining the physics is because new math is being generated to explain what we're seeing? So like we had the basic like add, subtract, multiply, divide, yes. It didn't quite explain what we saw, so we created new math, calculus, to then explain what we saw. And then we create new stuff as we're finding new stuff in physics. So is it more of a chicken and egg situation, or is there some inherent thing out there?
Okay, so let me put it this way. You know, all the math that you need for doing good physics, except for certain parts of it, was already created back in the 19th century, or maybe a little bit into the 20th century. And yet, we are able to do so much with that math. So you could say that math, for whatever the reason it was invented, proved to be enormously important for the kind of physics that we do today, except for string theory and so forth. So for example, if you look at, let's say, how new materials are created, that's a problem in chemistry, in material science, and those fields really need only calculus and linear algebra, not very much more than that. Well, if you want to do superstrings, on the other hand, you've got to go through all that very, very, very heavy math. So, do they go together? Yeah, one helps the other, and certainly at the very frontiers today, superstring theory and loop gravity and all those very cutting edge stuff, that is waiting for the right mathematics to be developed. But by and large, you know, the ordinary scientist, she can get along with math that was developed in the last 150 years. Yeah, we have.
Hi sir, my name is Mohammad Fadul Karim. I'm a physics student. So I have a 3-liter question. So what is the basic difference between calculus and mathematics? And the second question is that is new mathematics is now emerging or not? And the third question is that all physicists are good in mathematics, but all mathematicians are not good in physics.
Okay. So, all right, yeah, let's take that. So, yeah, look, calculus used to be, okay, mathematics existed before Newton. Newton invented a new branch of mathematics, which at that time was understandable to very few people, but now even before you enter college, even when you're in high school, you learn calculus, because things over time have become simpler and simpler so that you can teach them at lower levels of education. Your next question was, is new mathematics being invented? Sure it is. It's mathematics papers are pouring out, and they're becoming more and more difficult to understand. And so people who are in one branch of mathematics find it very hard to understand what's happening in the other branch of mathematics. What's happening in topology it cannot be understood by a number theorist, and vice versa. And the same thing goes for physics. There's a place which is called archive. In archive, hundreds of papers come every week, dozens come every day, and it's so hard to keep up with that. And your last question was, is a mathematician going to be a good physicist and vice versa? And the answer is no, it's certainly not necessary. These are separate skills. I have a mathematician friend, he's very good, but he doesn't have a clue about physics. He would fail his metric exam in physics, but he's super in mathematics.
Hi, sir.
Okay.
Sir,
but we'll give Regina a chance now. Anyone there, or should we proceed here?
Hoodbhoy, yeah, thank you very much for coming and sitting late at your place.
But they have a question.
Oh, you want to listen to that question?
Let's hear their...
Okay, yeah, I want to listen to your question. Head with the question then. I thought you want to say goodbye.
may I speak, sir?
Yeah. So should we have the question from here or from Regina?
question here.
No question here, sir, from your place, yeah.
Okay, go ahead.
Okay, sir. Where does you stand between the debate that math is invented or discovered?
So I'm glad you you asked that question. Okay, so this then takes me to the question of whether mathematics is invented or is it discovered. Let's take the number, so-called imaginary number iota, whose square is -1. Does it exist in nature? No. Do we see imaginary numbers? No. Therefore, I would say that it is something that was invented. On the other hand, if you were to ask Plato 2,500 years ago, he would say that all these things exist somewhere out there. And he called this the theory of forms. So let's take a chair. Can you define what a chair is? Well, you could say it's something that stands on 4 legs and has a back. Okay, but even within that, there are so many variations. But can you have a chair without a back? Yeah, why not? You can have a chair of this size, of this shape, of this material. So it's not easy to define a chair. However, what Plato would say is that somewhere out there, there is the perfect chair. And then everything on earth everything in our minds descends from that. So in that sense, the mathematicians who will say that yes, these ideas are already there somewhere, and that we are somehow recipients of that thought within ourselves. So they would subscribe to the idea of forms, whereas others, including Einstein, would say these are products of the human mind. And I would agree with Einstein rather than Plato on this matter.
Okay, sir. Then you said that the question about consciousness, and according to Plato, we could probe into the word of form through consciousness. So how they are compatible? And the last question is, why universe is so fine-tuned? If either like Dirac put it, the God is the mathematician of higher order.
So why is the world so fine-tuned? If the charge on the electron was a little bit different, atoms would not form, in which case you wouldn't have molecules, in which case we wouldn't be around. So what's the great, why has it happened? Well, one answer could be that then there would be no consciousness. There would be no one to understand the universe. It's only when those physical parameters are set that we can have consciousness, that we can have the existence of consciousness. So one way of that people have looked at it is using the concept of multiple universes, that there is an infinite number of universes, and that only in a very, very few such universes there would be the possibility of life to exist. That the life in one universe and the life in another universe could be entirely different from each other. They would never be able to communicate with each other. And so this is a hypothetical situation, one which is not verifiable, and science insists on verification. So therefore, these are nice speculations, but I don't know, and these are among the big questions.
Can I ask?
Right? So I think they have to go. Good. All right, so are we done, Regina?
Yeah, thank you, Dr. Hoodbhoy. I know it's getting late there. And thanks very much for your presentation. It was very enlightening. And we thank you again.
Okay, bye.
And see you next year, inshallah.
Okay, all right. Right.
Yeah. Can I ask a question?
हाँ चलिए अब हम अपनी बात कर सकते हैं.
मेरा एक सवाल था, excuse me. My name is Sadiq. मुझे ये पूछना था कि what is the role of mathematics such as discrete mathematics and theoretical physics, like physics के जो parts है, theoretical physics, particle physics, जो current emerging technologies है, उसमें उसकी क्या integration है और क्या role है और क्या role हो सकता है, और उसको एज ए लेमैन हम उसको कैसे समझ सकते हैं कि उसकी एप्लीकेशन कैसे होती है. बिकॉज पाकिस्तान में आपने देखा होगा कि मतलब उसको पढ़ाया तो जाता है बट उसकी सिग्निफिकेंस नहीं बताई जाती. जब छोटा था स्कूल में था, बस हमें बताया जाता था, हम क्वेश्चन करते थे लाइक इंटीग्रेशन का क्या कॉन्सेप्ट है, क्यों उसको पढ़ाया जाता है, कैलकुलस का क्या है, बस उसको ऐसे ही हमें बता दिया जाता था बट सिग्निफिकेंस नहीं थी. और स्कूल में ये भी था जैसे प्रोजेक्टाइल मोशन एंड ऑल, बट वो उसकी एप्लीकेशन उस तरह नहीं बताई जाती जैसे अब इंटरनेट के एरा में हमें समझ आती है, हम जो खुद सर्च करके देखते हैं.
भाई मुझे भी मैथमेटिक्स से बड़ी नफरत थी स्कूल में ना. टीचर आता है 2x + 7 = 3, फाइंड x. क्यों भाई, x से मुझे क्या, y z ये क्या, ये आपने ये इक्वेशन ऐसे ही गाड़ दी. तो आई हेटेड इट. मैं कोशिश ये करता था कि उस क्लास में मौजूद ही ना हो, और जब साल के आखिर में नंबर मिले ना, I got 6 out of 100. बहुत बाद में कुछ अकल आई, कुछ समझ में आया कि इन इक्वेशंस से हमें मिलता क्या है और क्यों इन इक्वेशंस को लिखा गया, क्यों इन्हें जब आप इनको सॉल्व करते हैं तो उसकी सिग्निफिकेंस क्या है. तो बहुत बाद की बात है. बहरहाल आपका पहला सवाल क्या था?
मतलब ये जो मैथ की टाइप होती है, जैसे मैंने एक बार आपको मतलब एक सेशन में आपने सुना था कि आप डिस्क्रीट मैथमेटिक्स का बता रहे थे, तो हमारे यहाँ मैथमेटिक्स वगैरह पढ़ाई जाती है बट उसकी सिग्निफिकेंस, उसकी एप्लीकेशन.
भाई डिस्क्रीट से मतलब क्या? वो डिस्क्रीट इज अ वेरी टेक्निकल टर्म.
एग्जैक्टली. तो वो
डिस्क्रीट,
जैसे अब आजकल की टेक्नोलॉजीज में जैसे एआई में और ब्लॉकचेन में ये सब उसको उसकी एप्लीकेशन पढ़ाई जाती है, बट एज सच उसको समझाया नहीं जाता. तो लोग मतलब उसको स्टडी तो करते हैं, तो एक सिग्निफिकेंस वो बाद में बताई जाती है, बट ग्रास रूट लेवल पे उसका नहीं बताया जाता. एंड सेम गोज फॉर फिजिक्स ऑल्सो. तो मतलब जैसे मैं अपनी बात करूँ तो हमें प्रोजेक्टाइल मोशन ये सब चीज़ें बताई जाती थी, बट उसकी क्या सिग्निफिकेंस होती है वो सब.
भाई सिग्निफिकेंस मैं क्या बताऊं, हर चीज उसी पर मबनी है. उसकी तमाम साइंस की असास वो मैथमेटिक्स है. आजकल आज की जो गुफ्तगू थी वो उसी के ऊपर थी. आप कोई सी भी चीज लें तो उसके साइंस की, तो वो मैथमेटिक्स के ऊपर बनी हुई है. डिस्क्रीट मैथमेटिक्स गालिबन आपका मतलब है बूलियन लॉजिक, जो कंप्यूटर्स की बुनियाद है. जब आप कोई कंप्यूटर को प्रोग्राम करते हैं तो उसमें एंड और नैंड नॉर ये सारे फंक्शंस होते हैं. तो उसका जो एल्जेब्रा है वो बूलियन एल्जेब्रा कहलाता है. एल्गोरिथम्स उसी से बनते हैं. तो चलिए.
शुक्रिया सर, लाइक ऑलवेज वेरी इंस्पायरिंग. और जो आप जिस पैशन से मैथ फिजिक्स और ख़ास तौर पे क्वांटम बताते हैं, बहुत ही शानदार लगता है. कायनात के मतलब एक छोटा सा क्यूरी है मेरी, कि जिस स्टेबिलिटी और जिस फाइननेस पे एक फिजिसिस्ट देखता है इस पूरी कायनात को, सब एटॉमिक पार्टिकल से शुरू होके गैलेक्सीज की मूवमेंट तक और वुसअतों तक, तो इतनी शानदार मेंटेन्ड माइन्यूटली ऑर्गेनाइज्ड सिमेट्रिक केओस से जन्म ले सकती है.
देखें, इंतशार तो आपको नजर आता है ना. तो केओस तो इस कायनात का हिस्सा है. तो आप को कहीं ऑर्डर नजर आता है और कहीं उसका उलट भी.
अभी सर रैंडम थ्योरी भी है ना, तो रैंडम थ्योरी भी इसी नतीजे पे पहुंचती है कि द स्कोप ऑफ योर ऑब्जर्वेशन वो डिफाइन करता है कि रैंडमनेस आप किसको कह रहे हैं. एज यू इंक्रीज योर स्कोप ऑफ और आपकी जो पावर ऑफ ऑब्जर्वेशन बढ़ती जाती है, तो उतना आपको पता चलता है कि चीज़ें इतनी रैंडम होती ही नहीं है एक्चुअली. कायनात की अभी जो तस्वीर इन्होंने ये आर्मेटस 2 के से आई है ना कायनात की, हब्बल से, और उसके बाद वो जेम्स वेब से आ रही हैं, यानी कि 49 मिलियन गैलेक्सीज जो आपस में जुड़ी हुई हैं. तो दे शो ए सो ब्यूटीफुल पिक्चर ऑफ एनीथिंग बट केओस.
नहीं, देखिए वो तो बिखरी हुई हैं. ये कोई किसी तरतीब से तो नहीं है. जो है हम देखकर कि कायनात इतनी वसी व अरीज है, लेकिन इसके पीछे ऐसे तो नहीं लगता कि कोई मकसद से ये बनाई गई. अब है, और जो हमारी हिस्स है, जमालियात की हिस्स है, उसके तहत ये खूबसूरत हमें मालूम होती है. किसी और को, बंदर को शायद ना लगे, बिल्ली को ना लगे, लेकिन कुछ चीज़ें हैं जो हमें अच्छी लगती हैं. कोई बात.
The chaos is already happening out there. The holes are created, stars are created, bangs are being, big bangs are being created.
हाँ, जनाब.
सर मेरा ताल्लुक स्वाद से है.
हाँ.
और इतनी बहुत अरसे से मुझे ये ख्वाहिश थी कि मैं यहाँ आऊँ, आपसे मिलूँ, अपनी ये मेरे इनके जो सवालात है उसके मुताबिक मैं सवाल नहीं करता हूँ. मैं ये सवाल करता हूँ और जवाब भी देना चाहूँगा
कि हमारे खिलाफ इंटेलिजेंशिया जो है, और आप इस वक्त दुनिया की सतह पर और पाकिस्तान की सतह पर ख़ास तौर पर इंटेलिजेंशिया के नुमाइंदे हैं, और जो दूसरी किस्म के लोग होते हैं वो हमारे खिलाफ ये इल्ज़ाम लगाते हैं कि आपको अपनी साइंस से वो होनी चाहिए, फिजिक्स से, और इसके साथ आपकी वो यू शुड एक्सप्लेन वट एवर इज़ यूर, और आपको सोशल और पॉलिटिकल में नहीं होना चाहिए। लेकिन हम ये कहते हैं और हम ये समझते हैं कि उन तमाम चीज़ों की वो जो रहनुमाई है, हमें उनकी रहनुमाई करनी चाहिए। तो अभी जो दुनिया की वो है हालात है, वाक़यात है, सियासी वो हालात और वाक़यात और जंग और इसकी, अगर इनकी साइंसी लिहाज से और मैथमेटिक्स के लिहाज से कैलकुलेटेड और क्वान्टिफाइड अप्रोच हम न रखें और अपनी माशरे के और तमाम लोगों की रहनुमाई न करें, तो उनकी ये कयास अभी वाक़ हो रही है। तो अगर मैं थोड़ा सा
मेरा ख्याल है किसी और को भी मौका दें।
जी जी,
क्योंकि वक्त बहुत कम है, देर हो चुकी है। बात तो ठीक है। इंसानी ज़िंदगी की कई जहतें हैं। साइंस, मैथमेटिक्स वो एक जहत है, मगर इंसान की नफ्सियात वो एक और है। किस हद तक हम इंसान को बिलाखिर समझ पाएंगे फिजिक्स और मैथमेटिक्स की मदद से, ये खुला सवाल है।
सर मेरा क्वेश्चन ये है कि डार्कनेस और वैक्यूम में फिर क्या फ़र्क रहेगा? अगर हम ये सर आपने कहा था कि सन से हम तक जो लाइट आती है अकॉर्डिंग टू इलेक्ट्रोमैग्नेटिक वेव्स थ्योरी वो इम्प्टी स्पेस से होके आती है, बट अगर हम आइंस्टाइन की E=mc² के अकॉर्डिंग चलें तो एनर्जी इटसेल्फ मैस में कन्वर्ट होती है, मैस एनर्जी में। तो अगर हम सन से या डिस्टेंट गैलेक्सीज से या फार यूनिवर्स से जो लाइट हम तक आ रही है वो तो हर जगह पे है यूनिवर्स में, तो वो हर जगह पे एनर्जी तो है इलेक्ट्रोमैग्नेटिक वेव्स की शक्ल में। अगर इलेक्ट्रोमैग्नेटिक वेव्स की शक्ल में एनर्जी है तो इसका मतलब है मैस E=mc² के अकॉर्डिंग हम काइंड ऑफ, तो फिर हम उसको वैक्यूम क्यों कहते हैं? और फिर हम डार्कनेस को कैसे डिफाइन करेंगे? क्योंकि अगर हम बहुत टेक्निकली फिजिक्स में जाएं तो हम लाइट को पूरा इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम कंसीडर करते हैं, फ्रॉम गामा रेज टू रेडियो वेव्स। तो फिर डार्कनेस क्या सिर्फ विजिबल लाइट के एब्सेंस की कहेंगे या?
भाई डार्कनेस का मतलब है कि कोई फोटोन नहीं है। फोटोन की एनर्जी उसकी फ्रीक्वेंसी के साथ जुड़ी हुई है। E=h टाइम्स द फ्रीक्वेंसी। अब आप ये कह सकते हैं, ये इतना भी ठीक नहीं है कि जहाँ एनर्जी होगी उधर मैस है, E=mc², लेकिन इसकी जो असल शक्ल है ना वो R=g टाइम्स t है। तो एक फोटोन दरअसल अगरचे इसका मास नहीं है, लेकिन जब ये सूरज के पास से गुजरता है तो सूरज उसको अपनी तरफ खींचता है और वो थोड़ा सा मुड़ जाता है। तो वो नापा गया है और आइंस्टाइन की थ्योरी की तस्दीक इस तरह से हुई। डार्कनेस क्या चीज़ है? एनर्जी की अदम मौजूदगी। तो अगर आप ये बत्तियां बंद कर दें, अंधेरा हो जाएगा, फोटॉन्स इनसे हम तक पहुंच नहीं पाएंगे, ये उसको डार्कनेस कहेंगे।
अल्ट्रावायलेट रेज, इंफ्रारेड रेज तो यहाँ
अरे भाई अल्ट्रावायलेट कौन से, ये दीवारें हैं वो सब रोक रही हैं ना
सर। कॉस्मिक रेज तो होंगी, कॉस्मिक
रेज होंगी, वो आ जाएंगी, लेकिन मुकम्मल डार्कनेस तो कहीं भी नहीं है, कायनात में कहीं भी नहीं है। क्योंकि आप सोलर सिस्टम से बाहर निकलेंगे और जितना भी दूर जाएंगे, आप सूरज की गिरफ्त से निकलकर फिर किसी और सूरज की गिरफ्त में आ जाएंगे। तो सवाल आपका क्या है?
सर मैं ये कह रहा हूँ कि फिर हम डार्कनेस और वैक्यूम को किस तरह से
नहीं है ना, डार्कनेस कोई परफेक्ट चीज नहीं है। जहां भी आप होंगे कहीं ना कहीं से रोशनी आप तक, आपके ऊपर पड़ेगी। नहीं ब्लैक होल नहीं। अच्छा चलिए आगे चलते।
मेरा आपसे फोर्थ क्वेश्चन है कि जो मौजूदा हर साल नोबेल प्राइज़ मिलता है, तो पाकिस्तान में ये कब पढ़ाए जाएंगे? ये नोबेल प्राइज़ की जो स्टडी होती है हमारी बुक्स में हमें ये नहीं पढ़ाया जाता।
क्या?
ये नोबेल प्राइज़ फिजिक्स में हर साल मिलता है सर।
हाँ।
तो हमें कोर्स में ये नहीं पढ़ाते सर। बस हम आपने भी कुछ
अब आपको मार्का हक पढ़ाएंगे।
हाँ, मार्का हक हम पढ़ रहे हैं सर। यस सर। वही कह रहा हूँ ना सर, वही पुरानी बुक्स में हम वही पढ़ रहे हैं। मार्का हक हम पढ़ रहे हैं।
जी आप कुछ? अच्छा ओके, तो काफी देर हो चुकी है।
थैंक यू सर।